In this video, we're going to go over the specifics of each type of electrophilic aromatic substitution reaction. Specifically, we're going to go over that first step, the formation of the electrophile. So our first reaction is the halogenation of benzene. In these conditions, we have benzene, we have our halogen, we have our iron 3 halide, whatever our halogen might be. You can also always use iron 3 bromide if you would like, or iron 3 chloride. You can pick either one. Ultimately, the identity of your halogen molecule is going to identify what you end up adding to your benzene ring. And we're going to do this with chlorine and bromine only. So in our first step, where we're actually forming our electrophile, because as I mentioned before, the electrophile is not actually here in these reaction conditions. It's going to be created in these reaction conditions. So in this first step, we have our molecular halogen. In this case, we're going to use bromine, and it has tons of lone pairs here. And we also have our iron 3 bromide. So iron 3 bromide is going to be a Lewis acid. We have a partial positive on the iron, partial positive or negatives on the bromines. And that's going to be really attractive to these many lone pairs on the halogen molecule. So the bromine in the halogen molecule is going to create a bond to the iron, just a Lewis acid, Lewis base association. And what we end up with is a complex molecule where we've created a negative charge on iron and a positive charge on bromine. Now, hopefully, something that you remember is that bromine is not exactly electropositive. It does not enjoy having a positive charge. Bromine is actually very electronegative. So bromine is not going to be particularly happy about this. So this is actually the identity of our electrophile. And when benzene comes in for step 2, and it sees this unstable molecule that we've just created, benzene is actually going to be able to alleviate the situation a little bit by attacking the bromine on the end. Now, at first that doesn't make a lot of sense, because why would the electrons attack the neutral atom instead of the positive atom? Well, the reason that it attacks the neutral atom is that that allows the electrons in this covalent bond to go onto the bromine. This is a slow reaction, but it has a pretty decent driving force of taking the positive charge away from bromine. So we now have our bromine added on to our benzene ring. We have our carbocation, and we've also created this kind of weird molecule here where we have a negative charge on the iron. Now our next step is that we are going to deprotonate so we can reform the aromaticity. We want to take the electrons in this hydrogen atom that is beta to the carbocation, and create a new double bond between our halogenated atom and this other carbon atom. So what's going to happen, whoops, did not mean to just erase half of benzene. So what's going to happen is that the bond between iron and bromine is going to break. So the bromine can take the hydrogen, and these electrons can create a new bond between the two carbon atoms and reform the aromaticity. So the result of this reaction is that the bromine ends up taking the place of the hydrogen once it's been pulled off. And you have your aromatic ring back. We also have an equivalent of hydrobromic acid and an equivalent of iron 3 bromide. So this is a true catalyst because it is used in the reaction, but an equivalent of it is also produced so that there's no net use of the catalyst. So keep in mind that the main difference in all of these reactions is only in step 1 in the formation of the electrophile. So from here on out, we're mostly going to focus on step 1 of each of these reactions. Our first reaction is the nitration of benzene. This is going to have a benzene molecule. We have nitric acid and sulfuric acid. That's kind of a nasty combination. And we end up replacing a hydrogen atom with a nitro group, NO2. And typically, you're also going to see an elevated temperature. If you're just using benzene or an activated benzene, which we'll talk about more in another video for this chapter, you can keep it pretty low. So in this reaction, we're going to have our molecules of sulfuric acid and our molecules of nitric acid. And nitric acid is actually going to be protonated by sulfuric acid. So we're going to pick up a hydrogen atom and deprotonate sulfuric acid, which gives us this kind of weird intermediate molecule, and also the conjugate base of sulfuric acid, which I did not draw. But there's a driving force for the creation of this kind of weird molecule, the reason that we did not protonate here instead of where we did. And that's because we can take these electrons and form a pi bond between the oxygen and the nitrogen and kick out an equivalent of water. And this gives us our electrophile and the identity of our base that is going to deprotonate our carbocation intermediate later. So when you introduce benzene to this, benzene is going to attack this nitrogen atom and push electrons back up onto the oxygen so that you get the structure of your nitro group. And I think a lot of us tend to forget that the nitro group is not as straightforward as it looks. You have the nitrogen with a double bond to oxygen and a single bond to the other oxygen. So that puts a positive charge on nitrogen and a negative charge on oxygen. In our next reaction, we have the sulfonation of benzene. This reaction uses sulfuric acid and sulfur trioxide, and it is actually reversible in the correct conditions. So we have our starting materials of sulfur trioxide and sulfuric acid. And we're going to see another kind of weird protonation happening here. We're going to use the electrons between one of the oxygens and sulfur to pick up a proton from sulfuric acid. And this actually gives us the identity of our electrophile and our base. Now from here, we can look at how this reaction is reversible. So if you take benzene sulfonic acid, which is the outcome of this reaction, and add water, and just enough acid to catalyze the reaction at a high temperature, you will end up with benzene and sulfuric acid. So this reaction is reversible as long as you have water and just enough acid to reverse it. Also, I want to point out that a common mistake for both nitration and sulfonation is to draw out the attached group incorrectly. And I want to point out that the nitro group is one hydrogen atom and one oxygen atom short of the acid that it came from. The sulfonic acid group, SO3H, is one hydrogen atom and one oxygen atom short of the acid that it came from. So that's our pattern here. We are losing one hydrogen and one oxygen in the formation of our electrophile. Our next two reactions are the Friedel-Crafts alkylation and acylation of benzene. And the electrophile formation in this reaction is actually really important to predicting the outcome. So for a Friedel-Crafts alkylation reaction, you're always going to have your benzene molecule and alkyl halide and aluminum chloride. And what you end up doing is replacing your hydrogen atom with an alkyl chain. Now, the tricky part about this is that we actually have a carbocation intermediate, and that's why understanding the formation of the electrophile can actually point you in the direction of the correct product. So let's say that you have 2-chloropropane as your starting material, and you have your aluminum chloride. This is going to be another Lewis acid-Lewis base interaction. The aluminum is partially positive, all of those chlorines are partially negative. So our chlorine over here is going to bond to the aluminum. This puts a negative charge on the aluminum atom, which is not great for a metal, and a positive charge on chlorine, which is highly electronegative, and therefore does not like to be positive. So what's going to happen in this one is that the chlorine is actually going to leave, and we are going to create a carbocation. Plus aluminum tetrachloride. So notice that our intermediate, again, is a carbocation. This is what the benzene ring is going to attack. So if benzene were added to this now, our product would have an isopropyl group coming off of benzene. This would be the bond that would be formed in the reaction. So knowing the identity of the carbocation is really important because this happened to be a secondary carbocation and could not be rearranged to anything else. But that's not always the case. Our carbocation electrophile is going to be subject to rearrangement. Your first step in any Friedel-Crafts alkylation reaction should always be to identify the carbocation that will form. It's actually really simple. You don't have to draw out that entire step that we just did to figure out what the carbocation will be. So let's take this example. We have benzene and 1-chloro-2-methylpropane and aluminum chloride. And we don't have to draw out that interaction between chlorine and aluminum in order to know that what's going to happen is the chlorine atom is going to leave and our carbocation is going to be this. And it's primary. And remember, anytime that you make a carbocation that is not tertiary, you should always be asking yourself, can I make a better carbocation? And in this case, we have a primary carbocation next door to a tertiary carbon. So yes, we can definitely make a better carbocation. We can take this hydrogen atom and shift it, which gives us a tertiary carbocation. So now that we know the identity of that carbocation, we can also kind of skip all those mechanistic steps if we understand how they work and draw our benzene product. So this is going to be the carbon skeleton that ends up attached. If you don't understand how this reaction works, then what you would probably draw on a quiz or an exam if I gave you this problem would be this. And that product might form a little bit, but it's going to be a very minor product, and this would be our major product. So understanding how the electrophile forms in a Friedel-Crafts alkylation is very, very important if you want to get your answers correct. So there are also some alternate alkylation methods out there. And these are basically almost any conditions that could create a carbocation. So for example, if you have an alkene and hydrofluoric acid is a weak acid, and fluoride, the conjugate base, is not a particularly great nucleophile. So if we pick up what we learned back when we did addition reactions to alkenes, you might remember that you can protonate an alkene. And due to the Markovnikov rule, you're going to put the hydrogen on the least substituted and put the carbocation on the most substituted. And that gives you an electrophile to attack. So our product would be this. Now, looking at this next one, we can do, again, what we talked about previously. We don't necessarily need to draw out all these arrows and stuff if we understand how the carbocation is forming. So if we protonate cyclohexene, we know that our carbocation that we form is going to be this, which means that when benzene attacks it, we're going to end up with benzene attached to cyclohexane as our product. And then one more, this uses boron trifluoride. This is not really a method that we've seen before, but it does form a carbocation, and in this case, you're going to consider the alcohol as a leaving group, essentially. And this is also going to create the same carbocation that we had in the previous step. And therefore, our product is going to be the same. So these are just alternate methods of alkylation, and all of these would also be subject to carbocation rearrangement. Now, our last type of electrophilic aromatic substitution is the Friedel-Crafts acylation. In the first step of our formation of the electrophile here, the chlorine of our acid chloride is going to attack the aluminum in a Lewis acid Lewis base interaction, just like we've seen before. And this is going to create a molecule that we haven't really seen before. The electrons on the oxygen of the carbonyl are going to form a bond between oxygen and carbon, and we're going to kick out the aluminum tetrachloride. And this gives us a species that we haven't learned before, which is called the acylium ion. So the acylium ion is actually our electrophilic species here. So when benzene attacks, you can push the electrons up onto the oxygen when benzene attacks the carbon. Or you can look at a resonance form of this molecule where you put the electrons from this triple bond onto the oxygen. And that puts the positive charge on the carbon, which makes it very clear what the structure of our electrophile is and what that's going to look like when it's attached to the benzene. So here is your electrophile, and aluminum tetrachloride is the identity of your base. In this last part of this chapter, we're just going to talk about how to synthesize acid chlorides real fast, because this is something that we haven't yet learned to do. So I want you to remember that in, I think, the end of OChem 1, you learned that you can take an alcohol and react it with thionyl chloride or phosphorus pentachloride, and you would end up replacing the hydroxyl group with the chlorine atom, creating an alkyl halide. Now in this class, we're going to see that you can do the exact same thing with a carboxylic acid, and the OH group will be replaced by a chlorine atom just like it was before. The only difference here is that we have a carbonyl compound, but the overall change is still the same. So you're definitely going to need this for a couple reactions in this chapter.